Will this pump cavitate? It's operating at 30 gallons a minute. There's an elevation rise of 20 feet. It's an 1.5 inch diameter pipe, water at 60 degrees Fahrenheit. The total pipe length before the pump is 30 feet. The pump requires 7 feet of net positive suction head, and the Darcy friction factor is 0.021. What we have to do is we have to go in and draw our control volume. And let's bring up the pen there. And we need our control volume to terminate right where the fluid comes into the pump. So there's 0.1. There's the suction side of the pump. We're going to look at that flow as it goes through there. We're also going to have to use the energy equation. So we got to make a couple of assumptions. To use the energy equation, the first assumption, we need a steady flow. There's nothing in the problem that states that it's unsteady. Second thing we need is incompressible flow. Everything is incompressible. It's water. Liquids are generally incompressible. Not a problem there. Last one is we need a constant temperature flow, and there's no temperature data, so it should be fairly easy to make that assumption that there is no temperature change. So now let's look at the energy equation. Pressure over gamma, V squared over 2G plus Z at 0.1 is going to equal to all of this stuff. Now I'm not going to write 0.2. I am going to write S for the suction side of the pump, because that's where we're terminating. Plus the head of the turbine minus the head of the pump plus the total frictional head. Let's look at this and knock out the low-hanging fruit, the things that are going to be easy to get rid of. There's no turbine, there's no pump inside this control volume. Because we've drawn a control volume, it terminates before the pump. We're going to set Z1 to be equal to 0. 0.1, surface of a large tank, 0. Can't get rid of that pressure, though, because we are going to have some pressure difference between the two of those. So now looking at that, we're left with pressure over gamma at 1 is equal to pressure on the suction side plus the velocity on the suction side plus the height on the suction side plus the total head loss. Now I want to calculate out what the net positive suction head available is, because I need to have more net positive suction head available than 7 feet. If I'm under 7 feet, this is going to cavitate. I'm going to add the vapor pressure head. I'm going to subtract the vapor pressure head. Now by doing that, I can take these three terms here and turn that into net positive suction head available. So as I do that and rearrange my equation, net positive suction head available will end up being pressure over gamma minus PV over gamma minus Z at the suction side minus the total head loss. So I know pressure at 1 because it's atmospheric. I know the suction side because that was given to me. What I do have to do is I have to look up what the vapor pressure is, and then I have to calculate out what the total head loss is. I'm going to calculate out the total head loss the exact same way I've done it for every other equation, every other problem that we've done. But once again, we got to remember, I'm dealing with a small control volume, just everything up to the pump. Now, in the context of a larger equation, we'd have to end up doing this twice because we need to know what the head loss is just up to the pump, and then we'd have to find the head loss for the entire system. First, let's go into our book. We'll look up what the vapor pressure of water is at 60 degrees C, and that's 0.226 psi. Absolute. We need to remember this is an absolute pressure. Now, we're going to want to convert it into feet because we're typically using that. So if I multiply this by, actually let's just write this out. So that's per square inch. Well, I know I have 1 foot. Actually, I have 12 inches is 1 foot. I want to square that, so I have square inches over square feet. And what I'll get here is the vapor pressure is 32.5 pounds per square foot. And so we're going to have to come back to that. So, H total, how do we calculate that? Well, H total is our Darcy-Weisbach equation. V squared over 2G, FL over D, plus the sum of the K's. I've already given you F in the problem, so we just need to go back and calculate out what the sum of the minor K's are. So let's roll back and look at that picture. We've got 0.8, 1.5, and 10. This one's nice and easy since I've given you all of that. So the sum of the minor K's, if we add those together, the sum of our K's will be 12.3. And so we are going to have to calculate a velocity, and then we have everything else. Our velocity is Q over A. Our Q value is 30 gallons per minute. Going to need to convert that to cubic feet per second, so 0.0223 cubic feet per second is 1 GPM. Conversion factor out of our book. Pi over 4, and now we need diameter squared. It's 1.5 inch pipe, so we'll just divide that right by 12 to put it right into feet, and we'll square that. When we bash these numbers out, you'll get 5.45 feet per second. And we'll go back to H total. So V squared, 5.45 feet per second, divided by 2G, English system, so 32.2 feet per second. Multiply that by FL over D. F is given in the problem, 0.21. L, we have 30 feet of pipe, because we're looking at the amount of pipe from the start to the finish, divided by our diameter. Once again, 1.5 divided by 12 to put it into feet. Add the sum of the minor K's, 12.3. We add all that together, and we have a total head loss of 7.99 feet. So let's go back to our equation. So NPSHA in the system is pressure minus the vapor pressure head. So the pressure at 1, we need to convert that over, because typically we're using 14.7 PSI absolute. And that's also 2117 pounds per foot squared. Subtract from that the 32.5 pounds per square foot of our vapor pressure head. Divide that by gamma, gamma of water, 62.4 pounds per cubic foot. As I take a look at that real quick, that's going to leave me with units of feet, which is what I expect. So that's good. And then we've got minus the height. So that pump is 20 feet above the surface of the fluid. Minus our total head loss, 7.99 feet. So if I go and I calculate that out, bash those numbers into my calculator, I get 5.41 feet of net positive suction head available. Now, I have 7 feet of net positive suction head required. So my pump needs 7 feet of net positive suction head to operate without cavitating. I only have 5.4 feet available. What does this mean? Pump's going to cavitate. Pump will cavitate. So this is not a good way that we have it set up. So what can we do? Well, we have to increase the amount of net positive suction head available. So how do we increase that? Well, we either increase this number or we decrease one of these two numbers. That number is a little bit hard to, this first one's a little bit hard to increase. We can change the vapor pressure, but now we're starting to get really complex. These ones are easier. We either remove some of the friction in the system. Yeah, that one might be a little bit more difficult. The easiest way is right here, is if we lower the pump. So if we take that pump from 20 feet and move it down to 17 feet above the water, and we look at that, well, that's going to be direct 3 feet. We add 3 feet to that. That gives us 8.5 feet ahead. We're completely fine. In fact, you can just drop this down to 18 feet instead of 20 feet, and that's going to give you 7.4 feet of net positive suction head available, and things will work out fine.